Welcome back. So, in the previous corollary we saw maximal linearly independent subset contains n vectors. It is a basis. Now we are going to show minimal spanning set contains n vectors. Okay, we have a vector space of dimension n. Let S be V1 through Vk. Minimal spanning set. So you know it is a spanning set and it's of the smallest size. If S is linearly independent, then it is a basis already. Two bases have the same size, so K must be equals N. If it is not linearly independent, and if some vector is zero vector, then drop the zero vector because we don't need zero vectors, and you get a spanning set smaller than S. But note, our S was minimal spanning set. So this would contradict. So there is nobody who is zero. Now suppose S is linearly dependent and consists of only non-zero vectors. Then there is a vector Vj, the same theorem we use repeatedly, that is a linear combination of the preceding vectors. Further, we may drop such a Vj and still have a spanning set. This will again contradict minimality of S. You see, because S is the smallest spanning set of V. So we cannot have anybody who can be dropped, be it zero or somebody non-zero who is a linear combination of the preceding. We cannot drop anybody. Okay. So S has to be linearly independent, therefore it must be the basis. Therefore K equals N. Remark: a maximally linearly independent set is a basis. A minimally spanning set is a basis. Here is a nice corollary. If a vector space V has dimension n, then any subset of size m, a subset of m greater equals n vectors. So any subset which has more vectors than the dimension has to be linearly dependent. Why? Since vector space V has dimension n, then a maximally linearly independent set must have n vectors. That's what we just said. It is a basis. It must have n vectors. But if you are independent and have more than n vectors, that's not possible. In other words, a set with more than n vectors would have to be dependent. That's all we are saying. Likewise, if a vector space V has dimension n, then any subset fewer vectors than n cannot span V. Why? Since vector space V has dimension n, a minimally spanning set must contain n vectors because it is minimally spanning. So it has to be the basis, right? It must contain n vectors. So a spanning set of V cannot have fewer than n variables, right? So you cannot have less than n. An important theorem: if S is a linearly independent set of vectors in a finite dimensional vector space V, then there is a basis T for V that contains S. This is very important. You start with a linearly independent set of vectors. You can extend it to a basis. Okay. Let V equals V1 through Vm be a linearly independent set of vectors in the n-dimensional vector space V, where m is less than n. So we are linearly independent but smaller than the basis. Choose any basis W1 through Wn and throw it with the V's. So build a bigger set, S here, S1 here. Now notice W1 through Wn is basis. So it spans V, and S1 being bigger than W1 through Wn, it must span V. So we must be able to reduce S1 to a basis by successfully deleting those vectors which are dependent on the previous vectors. So V1 through Vm, notice, were linearly independent. So these are not dependent on each other. So it's the W's who are dependent on the previous ones. So the vectors from S1 which get removed are from among the W1 to Wn. That is T. So we are deleting some of these vectors. We don't know which one. But the point is T doesn't lose any of the V's. That is T contains S. So we are able to find a basis that contains S. Here is a nice concrete technique to extend a linearly independent subset of column space or row space to a basis. Let V be the column space or the row space. Let S equals V1 through Vm, non-zero vectors which are linearly independent. We only know they are linearly independent. So what do? The procedure for extending S to a basis of V is as follows. First, extend this set with using your, remember the natural basis, E1 through En, throw in it. And then you want to identify maximally linearly independent set. So take a linear combination of all of these vectors to 0. That's your second step. Third step, because of this, you will get an augmented matrix. Transform it to reduced row echelon form. The vectors corresponding to columns containing the leading ones will form a basis. Here is an example. So let V1, V2 be this vector and this vector. We want to extend it to a basis of the row space R4. For R4, you have natural basis E1, E2, E3, E4. Right? You throw it all of it. So what is S1? First V1, then V2, then E1, then E2, E3, E4. So you see these are 6 vectors in all. Step 2, form the equation x1 v1, x2 v2, x3 e1, x4 e2, x5 e3, x6 e4 being the 0 vector. Write it concretely. Remember v1, v2, e1, e2, e3, e4. All of that has to put together give you the 0 vector. From here, I get a system. You see x1. So I'm looking at the first 0 here. So x1 minus x2 plus x3 and that's it, equals 0. For the second 0, nothing here. x2, nothing here. x4, that's it, x2 and x4, 0. For the third 0, x1 minus x2 and x5. That's for the third 0. The last 0, nothing, nothing, nothing. Oh, here you go, x6. That's the only one. So that's your linear system. So form augmented matrix and transform it to its reduced row echelon form. That's your augmented matrix. Now we know how to transform. I've just gotten a 0 here. Negative row 1 plus R3, row 3. You get a 0 here. Now I have 1 here. You see, I want a, by the way, this process got me a 0 here. That's fine. And then that's it. That's it. All I want is, why am I doing this? Remember the reduced form. So that's a leading one. I'm trying to get a 0 above. I got the reduced row echelon form. Now, identify those columns with leading ones. So that's a leading one, so that's column 1. That's a leading one, that's column 2. After that, that's a leading one, that's column 3, and that's a leading one, that's column 4. So notice leading one, once you are done with this, you go to the next step and look for a leading one. After that, you go to the next step and look for the leading one. After this, go to the next step. So this is echelon, you see. So 1, 2, 4, what is this? 1, 2, 3, 4, 5, 6. 1, 2, 5, 6. Give me the leading ones. 1, 2, 5, 6 columns. That is V1, V2, E3, E4. Why are these E3, E4? Because remember, 1, 2, 5, 6. You see? So V1, V2, E3, E4. That's a basis. That's a basis containing V1, V2. All right. Theorem, let V be an n-dimensional vector space. A part, if S is a linearly independent set of vectors. So you see that's n. N, if you have n linearly independent vectors, then you already have a basis. Or if you have n vectors which span V, then it's automatically a basis. Proof of A. V is n-dimensional. Any maximal linearly independent set should have n vectors. Now S is linearly independent with n vectors. Can it span V? What if it didn't? There is a vector here which cannot be in here. So I can throw it in. That's linearly independent because it's not dependent on the previous ones. That's a contradiction because now you have one more element, right? We know that dimension is n, so any maximally linearly independent vectors can only have n, and here you have n plus 1. So that's no. So that's a contradiction. Why? So span of S has to be V, so S has to be a basis. So let's address question B. Question B, S is spanning V. It has n vectors. Since V is n-dimensional, any minimally spanning set must contain n vectors. Since S spans V, if S is linearly independent, well, it's already spanning. Linear independence tells you it's a basis. Well, so the only catch is, what if it is not linearly independent? Then first drop all the zero vectors. Then drop that vector which is a linear combination of preceding vectors. You did that and you got a smaller set that spanned V. But that's not okay. Minimally spanning set must contain n vectors. Now this has fewer than n vectors and it spans V. That's a problem. So S, the problem was we assumed what if it was not linearly independent. That is false. S has to be linearly independent, therefore is a basis for V. Here are the homework problems. I know this is a difficult section. Take some time and look over the questions. Until then, see you.